I guess I should have recorded that spiel. Oh well. Tell your friends. I don't have friends in this class. I know you guys should all be friends. Should all be hanging out, but you're not yet, but you will be. No thanks to me, I guess. So today, we're going to start chapter 6. The, I dare say, kind of exciting part about chapter 6 is it's the beginning of the end for hypothesis testing and confidence intervals. Okay, so we're going to do 6.1 and 6.2, what they're called, in the old textbook. So there's really only 2 more question types that we have to learn how to deal with. Okay, and so in chapter 5, we were dealing with means questions, right? 1 sample mean, 2 samples, but they're paired, right? So then we have matched pairs, or we have 2 independent samples that we want to compare the means of, right? So all those are relating to the mean. Whereas here now in this chapter, we're going to be dealing with categorical data, right? And so we're going to be talking about proportions. Oh, I meant to check to make sure that the volume was off. So we don't all slowly go crazy. There. Like that. So, oh, and just to give you some light at the end of the tunnel, there's only 7 assignments, 1 for each chapter that we're doing. So 6 and then 1 more, and then it'll be over. Sort of. So, when we're talking about, right, because we have to talk about all these different types of questions, right? And so when I'm talking about chapter 5, I'm going to call those means questions, right? And so for chapter 5, just as a whole, I'll call them means questions. And chapter 6 as a whole, I'll call them proportion questions. Or proportions, maybe. Leaving room for multiples. Because categorical data, thinking way back to chapter 1, right, where we said, okay, categorical data, we've just got counts in each category, right? And we've looked at how do we deal with that in the lab, right? We just make a table of these counts, and then we can make bar charts if we want to of the heights of these counts. And so categorical data, we analyze it with proportions. Okay. So for chapter 5, we talked about means, and now in chapter 6, we talk about proportions, right? The difference is numerical data, categorical data, right? How do we analyze both? So what's nice about proportions is, 1, the formulas are way simpler, right? There's way less information that you need to plug in the formulas, so that's nice. But also, we're pretty familiar with hypothesis testing and confidence intervals now. And so even just looking at the formula sheet, you can probably figure it out, right? Given some key kind of definitions. But we're just going to keep doing hypothesis testing, keep doing confidence intervals, but for proportions now. Okay? And so just like before, right, we know we have to keep track of, okay, population information over here, sample information over here, right? We're going to have a population proportion and a sample proportion. And so I'm going to use a lowercase p for a population proportion, which kind of goes against my rule of thumb where I use Greek letters for the population. P is pi, right, in Greek letters. which I'm hesitant to use just because pi is something else, right? Pi is a number. And so you can definitely go ahead and use pi if you want to, but I'll be using p just so it's clear. Okay. And so this is the only time that I'm going to use just a normal letter to denote a population. Okay. And then for the sample proportion, I'm going to use p hat. Right. Remember the sample mean was x bar. Right. We can't use p bar because anything with a bar over it is an average. Doesn't really make sense, right? And so that's why we had to adopt the hat instead to make sure that we're talking about, okay, well, this is a proportion. And so, oh, so zoomed in here. Make my pen smaller. We can't use p bar since that would be the sample mean of p. Just as a little side note, right? Why we had to develop this other notation. So use p hat, which is a p with hat on it, for sample proportions. What's kind of cool, there I said it, it's cool, is that even though we're talking about categorical data, right? So we've got these counts and categories and some proportion in each category, right? A sample proportion, as long as some conditions are satisfied, will also follow a normal distribution, which is kind of weird, right? And so that's why I'm going to put more emphasis on checking the assumptions for proportions than I ever did for means, right? We didn't really check assumptions at all. We just went ahead and did our hypothesis test willy-nilly, but that's because what are you going to do? Your sample size is too small. Can't make it bigger, so, right? And so here, there are some key things that we just have to check to make sure that we've satisfied some assumptions before we go ahead and assume that it follows a normal distribution. Okay. First, let's talk about what p hat is. P hat is the number of successes in a sample over the total sample size, right? And so 4 out of 5 dentists, right? 4 dentists agree out of 5 answered, that kind of thing. And so it's that kind of question. Right? So we'll talk about the test results, right? Which questions did you choose? You had 4 categories to choose from. 1 sample mean, sigma known, 1 sample mean, sigma unknown, matched pairs, or 2 independent samples, right? And so we'll talk about those categories and then which one was your favorite, as in preferred to answer. Might not be your favorite, but I'm gonna call it that. You decided to do one. Okay, fine, it's matched pairs. You guys were awesome on the test. More about that later. I haven't marked them. Don't get your hopes up, but I will. It was just too much. I had to admit defeat last night. Couldn't do it. So we've got p hat. So that's just going to be our sample proportion. What's nice about p hat and finding p hat is I just have to tell you, okay, 40 students out of 120 like the color blue. Now you've got your sample proportion, right? 40 out of 120 or whatever I said. In one ear, out the other. So number of successes over your total sample size. Just as a little side note here, it's easy for me, hard for you, because I've got the little explanation of why p hat follows a normal distribution. This is not something that I'm going to test you on. Remember, so for the sampling distribution of x bar, we actually used it on this test, right? And you'll use it on the final. For p hat, no, we just go ahead and assume it. And so that's why it's just in the margin. Might be fun to talk about though. So as long as our sample size is large enough and all our observations are independent, then we can assume that p hat follows a normal distribution with a mean of p, so it's centered on the population proportion, and a standard error of the square root of p times 1 minus p over n. One thing that we've talked about when we talked about binomials, right, which was way back, was that, okay, well, 1 minus p we usually just denote as q. I've got that in the notes here, but I'll just add another note. Q equals 1 minus p. Because to save a little bit more writing, I'm just going to use Q, but it's your job to know that Q is 1 minus p, and that's on your formula sheet. So let's have a look at what your formula sheet looks like. So I've got it here. Since you're getting kind of hand-me-downs, it's possible that the order has changed a little bit. Like I think recently I bumped the confidence interval to the top. Why did I do that? No, I thought I bumped it to below. Yeah, should be below. I posted an old version. All the formulas are here. Sometimes, depending on my mood, I guess, I do confidence interval down here, hypothesis testing block up here. You have to be flexible. All the information is the same. I don't change a thing. Just the order. Okay. So if you have a look at your formula sheet, then we've got a formula for the confidence interval. We've got a formula for setting up our null and alternative hypotheses, right? And wouldn't you know it? We're back to calculating z-scores. Z-scores, we already know how they behave. We know to use the z-table, right? So there's nothing new here. We're just going back to the z-table for proportions questions. So that's kind of fun. And then we'll be able to calculate a sample size, which we'll talk about later. But which we did for means questions too when we had sigma known, but just briefly. And so, like I said, what's nice about proportions questions is how little information we actually need to do all these things, right? And so to get your p hat, you have to have your number of successes over your sample size, right? But that's only two things. And then you've got your p hat for your confidence interval, for example. Z star, you know how to find, behaves the same way as all the other Z stars. P hat again, Q hat is 1 minus p hat. And then n is your sample size, which you already needed to find your p hat, right? So there's very, very little information that you need to build a confidence interval for a proportion. For hypothesis testing for a proportion, for means, right, we talked about mu in our hypothesis. Now we're talking about our population proportion p. Same idea as one sample means problems. Right, where we had one sample of information and we want to compare it to some value, right? Now we've got one sample of information and it just happens to be a proportion that we want to compare to some hypothesized value, right? And so that's where your P naught is going to come from. To calculate your Z, it behaves the exact same way, right? How far is your sample proportion from your hypothesized proportion? Taking into account the standard error. Notice that this square root is different from this square root. So we didn't have that in the means problems. In the means questions, whatever was here in the confidence interval was down here in your t, right? But now for proportions, they're slightly different. So here you've got p hat, p naught is from your null hypothesis, and then the square root of p naught, q naught is just 1 minus p naught over n, then square root it. Okay. So if I just gave you this formula sheet, right, or these formulas, I am very confident that you will be able to build a confidence interval and do a hypothesis test fairly easily, right? So we'll go through it together, of course, but that's why I say, well, for assignment 6, you have all the tools that you need to figure it all out, but we'll finish the 2 sample proportions on Monday, which is question 2 on there. Oops. Any questions so far? So like I said, we're going to spend some time checking the assumptions first. So for proportions questions, we have this added step of checking the assumptions. And I can't remember. Did I make you check assumptions for the binomial? NP hat has to be greater than 10. Does that sound familiar to one? I'm getting shakes from everyone else, though. I don't know. Like, no, you didn't teach us that. All right. Maybe I did, maybe I didn't. We'll see. I felt like I did, but anyways, we'll talk about it again. But the conditions are the same, right? And just what's nice, I know it's hard to talk about the binomial. We thought we'd forget all about it. It's going to come back on the final, right? But what's nice is that these assumptions are the same as for the binomial, or very similar. So to check these assumptions, first, there's kind of 2 phases. So we have to have independent observations. And to check that, we have to make sure that we have a random sample, right? So everyone's randomly selected in here. And then the next thing we have to check is that we have less than 10% of the population. And so the idea being, if you've collected too much of the population, then there's bound to be observations that are not independent of each other, right? And so for me, I would say if you're lucky enough to have a huge sample size, congratulations, just take it and run with it. Maybe say something like, it's possible that the 10% condition is being violated, right? And so instead of thinking about these as checking your assumptions, it's more about, checking your assumptions, but also just stating your assumptions. Here are some things that I'm assuming when I'm going to do what I'm about to do, right? Do the hypothesis test or do the confidence intervals. And so some of this stuff, we just make it up, right? If the question doesn't say you collect a random sample, then you have to assume that it was a randomly selected sample, right? And so then you have to say, I'm assuming that the sample was randomly selected, right? So it's more about kind of just state all your assumptions, all the things that you're assuming before you head into this. And then it's up to the reader to decide, well, are those assumptions reasonable or not, right? And so as a buffer, I always start with, it is reasonable to assume that blah, 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 just so they can't argue. So we want to have a sample size that's large, but not too large, so not taking up too much of the population. But like I said, if you have a large sample, then who cares? I shouldn't say that, but better to have large samples. Okay. Second phase of our assumptions is to check the normality condition. And so here is where we go the other way, where we have to say, okay, well, our sample size has to be large enough to be able to detect these differences in the proportions, right, that we're trying to detect. What's tricky about checking this assumption is they're going to be different depending on if we're about to do a hypothesis test or a confidence interval. Okay. And so what you'll do at the beginning of a question is just read through and figure out, okay, am I going to be doing a confidence interval or a hypothesis test, or maybe both? Right. Spoiler alert, on the assignment, you're going to be doing both, so you're going to have to check both, right? But on the final exam, it's only going to be one of the two, right? So there's two proportions questions on there. One's a confidence interval, one's a hypothesis test, and you have to know which assumptions to check. And so if you're about to do a hypothesis test, what you have to check is that you're expecting to see at least 10 successes and at least 10 failures. Okay? And this is based off of your hypothesized value, right, from your null hypothesis. And so, and the idea is you have to have a large enough sample size to be able to detect. If you have a small proportion here that you're trying to catch, then you have to collect a really large sample to be able to pick that up. As a note, these conditions will always be satisfied, right? Either in the beginning we argue that, yeah, they're satisfied, or here, yeah, you're going to go through, you're still going to have to check them and make sure that they're satisfied. They'll always go through, right? Because if you tell me that, no, these assumptions aren't satisfied, then you can't do the question technically, right? But you'll always have to do the question. So it's just a matter of a hoop that we have to jump through. And so what you do to calculate the expected number of successes is you take your sample size times your hypothesized proportion and just make sure that it's greater than a count of 10. Same thing for your expected failures. You take your sample size, multiply it by 1 minus P naught, right, which is your Q naught, and make sure that it's more than 10. And then same idea for confidence intervals, and this is where it would be the same for binomial question. Oh, I remember, it was the normal approximation to the binomial. See what happened? That's when I had you check it. I remember. So I did. Anyways, they'll be the same. And for the same reasons too. So we have to have at least 10 observed successes and at least 10 observed failures, because if you remember in the confidence interval formula, there were only p hats, well, and q hats, but that's 1 minus p hat, right, and n. So there was no hypothesized proportion in there, right? And so that's why we have to use n times p hat. But if I've given you, 40 students out of 120, that's 40 successes. So 40 is more than 10, great. And then you can calculate how many failures you have. And so if you want to, you can use this formula, or you can just say, well, that's this many successes and this many failures. Both are greater than 10. Down here, I've got this note. Q is 1 minus P, or the probability of a failure. And then I've got all these guys here. They're all the same. And then I've told you that all of these, right, Q hat was 1 minus P hat, Q star is 1 minus P star, Q naught is 1 minus P naught, right? I just summarized it as Q is 1 minus P on your formula sheet. So it's on there, but I do, especially now at the start of this chapter, I know I'll get a lot of questions. How do I find Q? 1 minus P, whatever Q you want to find, it's 1 minus the P. This condition makes it so that the smallest possible sample size that you could have is 20, right? But that means you have to have 10 successes and 10 failures. right? It's really hard to get 10 successes and 10 failures right away, right? And so you have to keep sampling until you have 10 successes, or at least 10 successes and at least 10 failures. Right? So if you're trying to detect a really small proportion, you can see why you would need to have a really large sample to satisfy this condition. Any questions? Oh. So let's talk hypothesis testing then. So the idea stays the same, right? We've got some sample information. We want to compare it to some value, right? We want to have some formal hypothesis. And so remembering that you're talking about the population proportion P, and your P naught is going to be some number. P is a proportion. Oh, what the? P is a proportion. And so a proportion only goes between 0 and 1, right? Because remember, a proportion is a probability, which is essentially the same as a percentage. A proportion times 100 is a percentage. And so you have to keep that in mind, that all your P's have to be between 0 and 1. So all P's and Q's must be between 0 and 1. No more P's and Q's for him. Okay, so that's something to keep in mind, right? When you're calculating these proportions, they have to be between 0 and 1. Okay. All right. In step 2, where we do the test, right, we've got, well, we just take our P hat, our P naught from our hypothesis, and then over the square root of P naught, which is the same as this number, and then 1 minus P naught over N. And then, just like before, when we just kept calculating T's, and then once we had the T, it behaved the same way. Right now that you have a Z, it just behaves the same way. You use the Z table to find your P value. Right? Even though it's been a while, but we know how to do it, right? And so one thing that might come up here, especially in proportions, is, well, if you find the area in one of the tails, that's your one-sided p-value, right? If you need a two-sided p-value, you just take the one-sided p-value and multiply it by 2. What's nice about the t-table before, right, is just gives you, well, you just have to choose between one-sided or two-sided p's. Now you have to go that extra step and say, okay, do I need to multiply this by 2? And then I just kept the same blurb. Hopefully there was no typo in there. Who knows? I don't actually read these. Just rolls off the tongue. So now, once you have your p-value, right, we draw our conclusion the exact same way, right? Compare your p-value to your alpha level. If it's less than the alpha level, then you have enough evidence to reject H naught. If your p-value is not less than the alpha level, then you don't have enough evidence to reject H naught. Right? Same as always, NBD. Here's you guys. And don't worry, you'll stay in my notes forever, or until I revise them. So you guys in my other section from the morning. So 2 sections of stats in the winter term of 2018-19. That's your shout out. That's as good as I can do. Wrote a test where they were given a choice of 4 questions from the following types. 1 sample means sigma known, which I'm just calling known. 1 sample means sigma unknown, which I'm just calling unknown. Matched pairs, paired, 2 independent samples, which I'm just calling 2 means. They each selected 2 of the 4 questions to complete, as you might recall. And so a summary of the question types chosen is shown below. So I had a total of 78 students write the test. Okay. I dare say that you guys missed out a little bit because my other class had one on meerkats. It was a riveting test. And you guys just had what, Ronaldo at the coffee shop, which I think was pretty clever. I was like, well, I have some time. I'll make a separate test for you guys. But also because I had a heck of a time thinking of an appropriate occupation for a meerkat. I was like, I think I've already used mortgage broker, and I want some alliteration in there too. So it gets tricky, but anyways. So you guys got the coffee shop instead. Here's where we kind of run into a little bit of a roadblock, not too big of a deal, right? Because everyone wrote 2 questions. So now the number of questions being answered is 156. And so, so there's a total of 156 questions, but really I'm only sampling from 78 students, or taking a sample of 78 students. I just wanted to show you guys the data. I assure you the questions that you'll actually do won't involve this much thinking about, okay, so 156 questions, blah, blah, blah. It'll just be, out of 156 questions, 48 students chose to do the paired question. Right? That's why I say it's sort of a winner. We'll see. So what we can do is we can calculate the sample proportions of each of these groups. And so sigma known was the least favorite, or at least that's what I'm judging by, which questions you picked. And actually the match pairs and the two sample means were pretty good. I wasn't expecting a lot of activity on this one, but you guys surprised me, so we'll see. And then sigma unknown, of course. So you guys notice that unknown and paired are essentially the same question? Just a little bit different. Right. So what I did, and also what you'll do for lab 7, right, is I just looked at these and said, oh, okay, so it looks like paired is the favorite. And I'm calling it the favorite, I don't care. If you picked it, it's your favorite. Right? It's the most commonly chosen question, but that doesn't sound as good. So it looks like paired was the favorite question. Right? And so I'm going to build my hypothesis around that. Right? I'm just going to say, okay, well, is there evidence that paired data is a preferred question type? And also, first, are the assumptions for inference satisfied? Meaning we have to check the assumptions, and then we can go ahead and do this hypothesis test. Okay. So let's talk about, well, what's our null hypothesis going to be, right? Because if you remember to check our assumptions, right, we have to know what our hypothesized proportion is. In this case, right, because for a null hypothesis, we're assuming that everything is the same, right? If everything's the same and we have 4 groups to choose from, right, I would expect to see a quarter here, a quarter here, a quarter here, and a quarter here. You've got the same thing going on the assignment, right, where we're comparing the proportion of males being born to the proportion of females. Now you've got 2 categories. If the proportions are the same, I'll let you take it from there. Right. then your hypothesized proportion would be that they're the same. Leave a little bit of mystery in there. But so that's kind of a common trick that we use is, okay, so for our null hypothesis, if all these proportions are the same or essentially the same, then we would expect to see 0.25, 0.25, 0.25. So, and I've got that summarized in your notes. Our null hypothesis is that P is equal to P naught, where we replace P naught with 0.25. So all I'm saying here is that P naught is 0.25. We could have rephrased this question, but because I wanted to show you all the proportions, right, I didn't want to leave those other ones out. But what we could have done is said, out of 78 students, 48 of them chose to do the paired data question. Right? And so is there evidence that more than half the class prefers to do matched pairs, that kind of thing? Right? So there's lots of different questions that we could form around this data set. All right. So I've thrown in, as part of proportions hypothesis testing, we've got this step 0 where we check the assumptions. The first one being, okay, do we have independent observations? And so here's what I mean by, sometimes we just argue that we do. So here I'm just saying, we will assume that the sample of 78 students, because that's how many people wrote the test, is a random sample of all students taking stats in the winter term 2018-19. I'm just saying, hey, here's something I'm assuming might not actually be true, mostly because you're all just in my classes, but still. And then, but so you just say that that's something that you're assuming. And then the 10% condition, also, again, I'm just saying, okay, I'm going to assume that 78 students is less than 10% of the population of all stats students. Only because you have to be in stats to write a stats test. So that's the only reason I put that qualifier on there. But, yeah. So here, you just kind of bungle your way through it. Say, here are all the things I'm assuming. Leave me alone. Okay. So now we're doing a hypothesis test. So we're going to check that we have at least 10 expected successes and 10 expected failures. We've got a sample size of 78, and our P naught, remember, is 0.25. So a quarter of 78 is 19.5. It is more than 10, so that's good. So it checks out. And so a sample size of 78, where the probability of failure is 0.75, is 58.5. Notice that these two will just add up to 78. So you could go that route too. Okay. So you're just gonna do those calculations. I like to throw in a little check mark there. Check, check. Great. Moving on. And as far as your assignment goes, right, because you're going to do a hypothesis test in part A and a confidence interval in part B, then you may as well keep going and check the conditions for your confidence interval all in the same go, just so you don't have to rewrite this chunk. So that's why it's good to just have a peek, see what's going on, what do you have to do, right? Confidence interval, hypothesis test, and only check the assumptions that you need to. So we're saying, okay, we've got the sample proportion. I don't know, I think it's pretty fun because typically in R, whenever I'm finding a p hat, I just call it p hat, but it's like pH fat. Does anyone remember? I don't know, there was a phase, there was a time when, I don't know, just funny. Makes me laugh every time. p hat. So I'm going to round this to 3 decimal places. What I'm going to do, so on the final, I'll try to make sure that you don't have to round, that it just comes out to some sort of nice number, okay? Or I'll tell you what you're allowed to round to. Okay, the thing is, because here, 0.3076923, rounding to 3 decimal places is fine, right? It's only if you have 0.00005 or something like that, you don't want to round to 2 decimal places because then it looks like you've got 0, right? So you want to be able to, you kind of broaden your decimal places depending on the number. Here we've captured that it's 0.308, right? So your sample proportion that we're going to use is 0.308, which was the 48 over 156. So p hat was 48 over 156. Next thing we're going to do is we're going to state our null and alternative hypotheses. And so my null hypothesis is that, nope, all these groups are essentially the same, no significant difference between any of them. And then my alternative hypothesis is that my proportion of those who chose the matched pairs question is actually greater than 0.25, making it the, like I said, the preferred question. So this is a one-sided test, right? But especially for proportions, you want to make a note. If you're doing a two-sided test, then you have to multiply your p-value by 2. To do the test, I'll zoom in here. We just plug and chug. So we've got 0.308 minus 0.25. For the longest time, I've been meaning to have a math party, plug and chug, but anyways, hasn't happened yet. I do have math parties, but not that theme quite yet. Anyways, I'll get there. 0.308 minus 0.25, and then again, you just reuse the 0.25 down here, and then 1 minus 0.25, and then over n, which is your 156. Z, remember, T's need to have 3 decimal places to match the table, and Z has to have 2 decimal places to match the table, right? So we have to round this to 2 decimal places. So we get a Z of 1.67. Not that big, right? So we're kind of not sure if we're about to reject the null hypothesis or not. So we'll go through and see what happens. Stay tuned. But as far as what's going on, right, now that we've got this Z score, we know Z follows a normal distribution centered on 0, and we've got a Z of 1.67. And we want to know if P is larger than 0.25, meaning we need the area in the upper tail. If we wanted to show that P was less than 0.25, we would want the area below this value. Doesn't really make sense because the area below this value is huge, right? So it's usually just the area in the tail. So this is the one-sided p-value. So to find your p-value, you're going to use your Z table. So using the Z table, we find the area to the left of 1.67 is 0.9525. right? So we always have to find the area to the left first, and then we can find the area to the right. So the area to the right is 1 minus 0.9525, which is 0.00. Oops. It's just 0.0475. Therefore, the one-sided p-value is 0.0475. If you're thinking about your conclusion, right, 0.0475 is less than 0.05. I didn't give you an alpha level, so it is less than 0.05. But you want to be really careful, and I've got a note about that over here. 0.0475 is just on the, it's really close to 0.05, right? And so if you're making big decisions based off of 0.0475, you might want to be careful, right? If you're going to make a recommendation that you buy millions of dollars of equipment based off of a p-value of 0.0475, might want to think twice about that, right? Here, because our conclusions, I mean, does it actually matter if matched pairs is the preferred question or not? No, not really, right? Just my pride, I guess. No, I have no idea how it relates to my pride, but anyways. So, right, so in this case, no, it doesn't matter, right? I'm gonna reject the null hypothesis, but you wanna be careful so that you're not just blindly rejecting the null hypothesis based off of a p-value that's not even that small, right? I've also got a note here, if you take it another step, right? What if this was a two-sided test? Then you would have to take your 0.0475 and multiply it by 2. All of a sudden, you have a two-sided p-value of 0.095. So then now you wouldn't be rejecting the null hypothesis, right? And so that's another reason why a two-sided test is the default, is because it just makes it a little bit harder to reject the null hypothesis, right? Because we've got this p-value happening in both tails. Okay. So it's just some p-value advice that you should kind of keep in mind a little bit. Not for the course, but for life. Right? You're using this stuff and you're using p-values that aren't really that small, but you're still going to reject the null hypothesis, right? You might want to write a little side note and say, oh, well, the evidence wasn't that strong, right? But here's my conclusion. I threw in the R code for this, just because. We can use the proc.test command. It uses X, which is your number of successes. It needs N, your sample size, and it needs your P naught, which is your hypothesized proportion. Right? I also threw in, well, in this case, I've got a greater than sign in my alternative hypothesis, right? So I added that in. And also here, I threw in correct equals false because this is just to get an answer that's close to what we would do by hand. There's lots of different ways that we could analyze proportions, and it just depends on how they're laid out. The Z-score is one of those. I like the Z-scores just because we're not going that deep, and we already know Z-scores, so why not use them? But this is just to try to match the calculations we've done by hand. Otherwise, it throws in a continuity correction, which we don't do when we do it by hand, but easy to do on the computer. So I just added the correct equals false. But if you don't have it in there, it doesn't matter. So your output looks like this. And so it's just saying, okay, here's a one sample proportions test without continuity correction. It's just trying to match in the lab, you don't have to have the correct equals false because you can just use whatever p-value gives you. But the p-value that it finds here is the 0.04805. Right. And so here's your p-value. This is your one-sided p-value. Right. Which is similar to 0.0475. Another thing to keep in mind, right, is that we rounded our p-hat from the beginning, right? And so we're going to lose a little bit of precision there. But 0.04805 is very similar to 0.0475. You'd be drawing the same conclusion. It does a chi-squared test, which is just a different way of testing proportions. And so here, this value here, it actually looks like a fancy x and then squared. And it's a chi, but we call it chi. And then so it's a chi-squared. I don't think we'll have time to get to chi-squareds, so you can all relax. But it's just hypothesis testing, so you can handle it. Just a slightly different calculation. And a different table. More printing for me, no thanks. And the environment says no thanks. We can draw our conclusion, right? Since our one-sided p-value of 0.0475 is less than our assumed alpha level of 0.05, this all should sound very familiar now, right? We have enough evidence to reject H0 in favor of H8. Therefore, there is evidence that paired data is the preferred question type, but technically all I can say is the most commonly chosen question, something like that. I don't know if it was your preferred type. I'm just assuming. No? Any questions? Okay. So, I thought I had a page break in here, but I don't. Let's do example 2 together. Example 2. Example 2 is very similar. Consider the previous example where only 25 people chose to do a one sample mean question with sigma known out of a total of 156 questions completed. So out of the 4 different choices, is this sample evidence that the one sample mean with sigma known is the least popular type of question? And so now, everything's kind of the same, but now we're just flipping the sign in our alternative hypothesis to show, well, is P for the one sample mean sigma known question, is it significantly less than 0.25? So we've got X is the number of successes, which is, oops, I forgot to check, 25. N is your sample size. We use 156. And our p hat, oh, I guess I can zoom out. Oof. All of a sudden my writing got so small. Our p hat if you want a formula, it's just x over n, but it's just going to be 25 over 156. .1602561, which I'm going to just round to 3 decimal places, 0.160, rounding to 3 decimal places. So already we're going to lose a little bit of precision just by rounding, but I'm okay with it if you are. I know you are. You guys love rounding. So, first thing we have to do, right, is we have to check our assumptions. And so, but in our assumptions, right, we have to know what our null hypothesis is, or at least what our hypothesized value is. So let's just jot down our null and alternative hypotheses first. So we have to talk about P, right, the population proportion P, and how it relates to 0.25, right? Because again, we're saying, okay, all these question types are all the same. Is this one less than all the others? So now we want to show, or we suspect, that P might actually be less than 0.25. So we have a one-sided test again. But by the sign, right, we're going to be in the lower tail instead of the upper tail this time. So for our assumptions, just to get some practice, they'll be the same, but just to get some practice in just writing out our assumptions, we have to talk about, okay, do we have a random sample? And again, just for simplicity's sake, I'm just going to talk about you guys, the students that wrote the test, instead of the 2 questions that you chose each were randomly selected. It gets wordy, right? So I'm just going to talk about the 78 students. If you're reading the assignment, right? So we hear that newborn babies are more likely to be boys than girls. Is this true? A random sample found 13,173 boys among 25,468 children. So here you would just say, okay, your sample size is 25,000. Were these randomly selected kids? It says a random sample found blah, 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 right? So yeah, it's random. So then you can just say stated in question or something. Right? For us, we're going to have to get a little crafty and say, we assume, we can even just say something generic. Take something generic out of this. We assume the sample was randomly selected. At this point in my marking of the final, am I actually reading your answers? No, probably not. So if you just have something that looks good, yeah, we assume the sample is randomly selected. Moving on. Yeah, that's fair. N has to be less than 10%. And so here, right, we're just going to argue that our sample size of 78 students is less than 10% of the population of students. I'll throw in my usual. It is reasonable to assume a sample of 78 is less than 10% of the population of stats students. I'm only throwing in the stats just because it's about a stats test, so obviously you have to be in stats to write this test. But besides that, I'm not really clarifying stats students at the college, stats students in Kelowna, in BC, in Canada, in the world. I'm just leaving it open. Here's an assumption I'm making. So, we're doing a hypothesis test, right? And so hypothesis test, I just shorthanded to HT, hypothesis test, since I'm introducing it here. And then of course, CI, confidential informant, no, confidence interval. So that's how I just shorthand those. But a hypothesis test is what we're about to do. We're not gonna, there's no mention of a confidence interval, so we're not gonna check the confidence interval's assumptions for this one. Later on when we do one, of course we will, but we have to check that n times p naught, which is 78 times 0.25, which I remember was 19.5, is still more than 10, surprise. NQ naught is 78 times 0.75. Is it 58.5 or? I think. Which is still greater than 10. Phew. Okay. Oh, I added a page at the wrong page. There. Here I'll just say the assumptions for inference are satisfied. You don't have to write that or anything. I'm just clarifying that at this point, I've checked all my assumptions. Now I can go ahead and actually do my hypothesis test. And so step one is to state my hypotheses. Which we already developed, so H naught is P is 0.25. HA is that P is less than 0.25. Again, we have a one-sided test. Step two is do the test. That's where we do our calculation. So we have to calculate Z is P hat minus P naught all over the square root of P naught Q naught over N. So we've got P naught, or P hat, sorry, is 0.160, right? That's our sample proportion. Minus P naught, which is 0.25, all over the square root of 0.25 times 0.75 over 156. 0.25 times 0.75. I'll just write these out piecemeal so that you can check your work. 0.16 minus 0.25 is negative 0.09 over the square root of 0.25 times 0.75 is 0.1875 over 156 divided by 156. So we have negative 0.09 divided by the square root of 0.00120193. One thing I will mention, because it will come up, if you forget to do the square root here, and just do 0.09 divided by 0.0012, you're going to get a huge z-score. Okay. So yes, big z-scores can happen, right? But more likely you forgot a square root. And so if you're doing these and you're getting these huge z-scores, then just make sure, go back and make sure that you didn't forget the square root, because I think without the square root, we get a z of something like 78 or something like that. So it gets huge, but you know what? Store in 1.09 divided by, 74.88, close enough. Right, so that's a huge z-score. So that's when I haven't taken the square root. But if I go ahead and do recall 1 and then take the square root, store that, negative, oops, guess I should write it down, negative 0.09 divided by 0.034668762. 0.09 negative divided by 2. I get a much more reasonable z of negative 2.595996918. If you're going through, as long as you've shown your values plugged in and then your final value, that's fine. Here, I'm just showing you all these little steps so that you can check your work. But just plugging in your values and then showing the end result is fine. So negative 2.60, right? Because z has to have 2 decimal places, so we have to round properly to 2 decimal places. Okay. Add another page. Can draw out the curve just to visualize the p-value, right? So now we've got a z, a z of negative 2.60. We want to show that p might be less than 0.25, and so we need the area in the less than tail, or the lower tail rather. This is your one-sided p-value. Using the z table, we find the area to the left of z equal to negative 2.60 is, my trusty one, negative 2.60 is 0.0047. Therefore, the one-sided p-value is 0.0047. If you had to find a two-sided p-value, you would just take this one, multiply it by 2, and that's your two-sided p-value. Now that we have our p-value, we can draw our conclusion. So step 4, same as always, is our conclusion. Since our one-sided p-value of 0.0047 is less than our assumed alpha level of 0.05, we have enough evidence to reject H naught. We have enough evidence to reject H naught in favor of HA. Therefore, I'll be so bold as to say, therefore, we can conclude one sample means sigma known are the worst. No. Therefore, we can conclude, I'll just say sigma known problems are, I don't know, the least preferred. That doesn't really make, you guys know what I mean. The least preferred question type. Any questions? So, next day we'll talk about the confidence interval, but like I said, you have the tools to go ahead and do it. And with the notes, if you didn't, I hope everyone got a copy of the notes, but you can go ahead, read through those. You'll be able to do the sample size calculation, and you'll be able to do the 2 sample proportions, but we'll talk about them on Monday. See you guys then. Oh. I've got 2. You can have this one. That one. Oh, it's okay. I am gonna go. So if you need a copy of assignment 6, just come with me upstairs and I'll grab you a photocopy real quick. Yes.